Hello, everyone. Welcome to the webinar today. Let's go ahead and get started. Today, we are talking all about false trips. And actually, this is the first webinar in a series of webinars that we're going to be hosting all about final element design and how to improve your safety without increasing false trips. And we're going to be presenting these throughout the fall. This is the first one, another one later in September, then continuing through October and November. But before we get started, if you have any questions throughout the webinar, please feel free to write them into your questions tab on your panel. I'm not the best at pausing and taking a moment to look throughout the webinar, but I'll save time at the end to answer any questions you might have, and we can go back into the slides if you need to. But today's webinar, we're going to, as I said, it's going to be the first of multiple webinars on final trips or false trips in final element design. And today we're going to be focusing on what most of you kind of already know. In many industrial processes, an automatic safety function is implemented using a remote actuated valve. You already know that that's kind of commonplace. The design objective for is that this SIF, or this final element assembly, trips the process if a dangerous condition is detected. At the same time, it keeps the process going when there's no dangerous condition detected. Because of that, often, most people are super focused into the failures that impact the ability for the safety function to do its job, to actually trip if there's a dangerous condition, which, yes, that is the most important part of a safety function, absolutely. But there are many applications where a false trip isn't a good thing either. There are times where it can just be an annoyance, but there are times where it's more than that. It can be a very costly annoyance, to even creating a larger problem or leading to a dangerous situation. Many of the heritage designs out there have pneumatic or hydraulic controls, and they actually are increasing the false trip rate. Oftentimes, the justification for that increase of the false trip rate is because we're working on improving safety. Yes, absolutely. If you put redundancy in your system, you are going to improve safety. But at what cost? Usually, it's the high cost of a high false trip rate. And that's not what functional safety was put in place to do. Our goal at exida and functional safety goal is not to have you have a high false trip rate. It's the opposite. We want you to be safe, yes, very safe. Those dangerous failures are very bad. We need to still absolutely focus on them. But we also want you to be reliable at the same time. And this webinar and the webinars to come are going to focus on how to design or implement your design in a better way and a more safe while still being reliable way. This webinar today, we're going to look at several different pneumatic designs. We're going to compare 4 different designs and show what their dangerous failure rate is, that big scary one everybody talks about. But we're also going to look at your false trip rates and the safety and probabilities for each of those designs. And we're going to compare all of them together and see that, just like in everything in life, there are pros and cons for each design and each assembly. And we'll take a look at what that means for you. For those of you that have not yet met me, hi, my name is Lauren Stewart, and I've been working with exida for over 8 years now. I'm in our mechanical sector. I'm a mechanical engineer here, and I help focus our mechanical, especially our final element customers, how to really implement functional safety into their design and how to go through their certification process as well. I see a couple of new faces or new names that I have not seen before. So just in case you're not familiar with exida, I wanted to let you know a little bit who we are before we get into why you're really here. But at exida, we are really focused to help you create and achieve both safety and reliability in solutions. And that's exactly what we're going to be talking today. That safety is very important, but also is reliability and how they really do go hand in hand. We have here at exida, we have lifecycle tools that can streamline your functional safety approach, your calculations. We do certifications and assessments and even help if you have over your comprehensive lifecycle services. No matter how big and tough your problems are, we have experts that can help you solve them. I like to say no matter where you are, where your products are coming from, where they're going to, where your customers are, we have somebody with functional safety, cybersecurity, and alarm management expertise close by, right in your back door. And I love showing this map because we're always popping up new locations. We just have, I think, 2 new ones on here since my last webinar. We have our Irish office and our Australian office now highlighted. So it's fun just to continually see our map growing. As I mentioned before, we have a complete suite of lifecycle tools, and they cover both the manufacturers of that equipment that's being used in these SIL systems, the whole way through to end users who's doing operation and maintenance with these products and devices every day. And last slide about exida real quick. exida, we are super proud to say that, be able to say that we are the global leader in functional safety certification. And even if we didn't have, even if we're newer to the ball game than others are, we are super proud of all of the hard work that we've been able to do and accomplished in these certifications. Oh, one more. I always throw this in because I love to tell my customers this. This is something I always say, come back to. It's very important. Here at exida, we always are researching the latest and greatest and ways to be safe and to be reliable. And we feel that there's no good holding that inside. We want to get that information out there. What good is it if we know how to be safer and not giving that out to everybody? So always come back. We're doing these webinars for free, blogs for free, tons of white papers that you can download for free as well. We are constantly publishing new books, going to conferences and colleges and trade shows and giving speeches on all of our research. So always check back to see what the latest and greatest in functional safety, and you never know, you might learn something. So let's get into why you're really here today. And I have a feeling it's not really to find out how to cause a false trip, but more to maybe find why you're getting false trips or how to solve a better final element design. So through this webinar, we're going to look at a few different designs. As I said, I think we're going to look at 4 different architectures and design of final element designs. And they're all going to include a spring return pneumatic actuator. Spring return actuators are commonly used in SIFs or the final element designs for your automatic safety functions, so that air supply failures are not dangerous. A lot of attention is paid to those failures, those dangerous failures that impact the ability of that safety function to perform if needed. If that dangerous condition occurs, you want your final elements to be able to shut down the process if necessary. So, as I said, most of the attention goes to those dangerous failures. And sometimes safe failures are kind of forgotten about or pushed to the side or swept under the rug. As long as you're calculating your dangerous failure rate, that's the priority. That's what you need to know, right? Well, yes, but we also want you to think of those safe failures, those false trips, because those aren't necessarily good things to have either. In many applications, a false trip, as I said, it can range from anything to be kind of annoying to very costly and annoying to creating problems down the line, adding up maintenance, and actually creating dangerous situations when your SIF cannot respond to a shutdown necessary if a demand occurred. So throughout this webinar and in the next upcoming webinars, we're going to be asking, what are some key issues in design that can cause a false trip? And also, how can false trips be reduced while still having that safety implemented? So let's look at our what goes into our major designs. So when we put together our final element assemblies, normally we're talking about a valve, an actuator, and some kind of control. Let's look at each of these individually, not together as an assembly, but each separate, and see how they can contribute to your false trip rate alone. So first, let's think of a valve. So we have a valve. It's your simple butterfly or simple ball valve, and it's just that simple mechanical device. There's nothing smart about it. There's no actuator, there's no solenoid, just your valve. It can't really decide to act on its own. It really doesn't have that many safe failures or spurious trips that could happen if you're talking about just the valve. It's pretty hard to find false trips there. Now, if we go to something, let's take off the valve hat and put on the actuator hat. Just looking at the actuator, forget the valve, forget the solenoids, everything else, and think, okay, this is a lot easier to cause a false trip. A false trip can occur when too much air leaks out or pressure is vented or lost. So this could be something even as small as you'll have O-rings or seals that are broken or missing or bound together and not performing their job right, leaking, and air is getting out. So it could be something as small as just O-rings. And so this could easily cause some false leaks or for some false trips. Next, let's take off the actuator hat and put on the control hat. We're talking about our solenoids and etc. Again, thinking of just those devices, it's pretty easy to have a false trip. The controls could tell the actuator to vent its pressure when it's not needed. And now, of course, there's other components that could be in your final element design, like you could have your volume boosters, your filters, your position monitors, all of those. And all of those that are included in your design need to be a part of your calculations and your SIL verifications. But I just wanted to highlight a couple of the key main contributors to false trip rates in your final element design. So when comparing final element designs, when looking at architecture, how do you know what's best? How do you know what's safest? How do you know what's most reliable? Well, I'm an engineer, so the best way to prove something to me is show me the numbers. And that's exactly what we're going to do in this webinar. We put together 4 different assemblies with 4 different architectures, all including a spring return actuator, a triple offset butterfly valve, a 3-way solenoid, and depending on the configuration, a quick exhaust valve or not, and filter regulators. We collected each of these individual devices, calibrated FMEDA's reports, which listed all of the safe failure rates, all of the dangerous failure rates, along with the proof test coverage for each device. And then we started putting them together in different configurations to figure out what we were looking for and what would cause our problems. So as many of you may already know, when we're talking about safety, we usually get into talking about the probability of failure on demand. This is usually known for low demand devices as PFD average. And this is one of those key main factors that the standard talks about, that you calculate, that you can figure out your skill level. In this PFD average calculation, if you've done this before, you know it's not just a simple little calculation, but there are a lot of things to consider, including 9 key variables. And with some of those variables, we had to make some assumptions for today's calculation. With those assumptions, we have, first of all, that as I said a couple of times already, I think you've gotten this, but a spring return actuator was used on all of the configurations. All of our solenoids were de-energized to trip. Our valve was a close-on-trip application. We decided to do a proof test once a year during plant shutdown. The average cost of a false trip for this plant was $500,000. The mission time for our final elements was that 15 years. We used a common cause or a beta factor for the 1 out of 2 devices of 10%, and any common cause failure rate dominated the 1 out of 2 results. And also, we assumed that whenever you received your final elements, you received your assembly, you put them through testing and commissioning, and you know that they are ready and willing to work, that you're not going to have an initial failure right out of the box. You've already tested, ruled that out. So with those assumptions, we were able to create the different architectures and look at both safety and reliability. So let's take a closer look at each one of these 4 designs. The first one being the simplest of them all, our simple 1 out of 1 design. We have just our spring return actuator on a triple offset butterfly valve, 3-way solenoid with our filter regulator. As you can see, we listed out each of the devices along with from the exida calibrated Prometheus with their failure rates for both safe and dangerous, along with their proof test coverage. We ran all of our calculations and entered all of our assumptions into Excelentia, and we were able to arrive at the safe failure rate, or that false trip rate, of 7.55 times 10 to the negative 10 failures per year. So if you're not familiar with functional safety, you might be thinking, okay, that number is very small. It's really hard to realize or visualize what that means. So another way of looking at that is to take your cost for your false trip and enter that into the calculation by giving you your false trip risk cost per year. So this configuration will end us costing us $3,307 per year. Okay, that's an easier number to understand. This operations, it costs $3,000 or $3,300 to operate it in regular conditions. Our dangerous failure rate, once again, that's that really important one, the one everybody pays really close attention to, is 1.34 times 10 to the negative 6 failures per hour. Again, that's a number that's really obscure. It's hard to grasp if this isn't something that you work in every day. But the bottom line is your PFD average rating or probability of failing on demand is a 0.0196. And if you use the tables in the standard, that comes out to a SIL 1 capability. Next, let's change the design a little bit. Let's look at still a simple 1 out of 1 on your valves and actuators. However, we're going to add an extra solenoid. We have a 1 out of 2 solenoid design here now. Again, we're keeping the same types of devices. The only thing we are doing is adding that second solenoid, and we reran the numbers. This time, we have a safe failure rate, or that false trip rate, of 1.27 times 10 to the negative 6. Or if you're looking at a false trip rate cost per year, we're looking at $5,563. Okay, it's kind of hard to see the failures per year and the difference in those numbers, but seeing the difference in the dollars and cents, that makes a very clear picture. This with our dangerous failure rate, remember that's the special one everybody usually pays attention to, is 1.19 10 to the negative 6. What does that mean? Bottom line, your PFD average is 0.0188, which equals a still 1. And you don't have to remember all of these numbers right now. I'm presenting all of the cases, and then in the end, we will use them all the numbers on one slide so we can compare and contrast. But just as a frame of reference, this has a slightly better safe PFD average, yet a much higher cost, or the false trip rate cost per year. Now let's look at a different design. It's very similar to the last one we just looked on. It's actually building upon that. So you take that same valve, that same actuator, still 1 out of 1 design, and now we're adding a quick exhaust valve to the 1 out of 2 solenoid mix. So we added our quick exhaust valves, we received the failure rates and the proof test coverage calculations from the calibrated FMITA. We reran them through Excellentia with all of those assumptions again. And we arrived at a safe failure rate of 1.13 10 to the negative 6. Remember, but that cost per year is $5,742 now per year. Our dangerous failure rate, the one that everybody pays attention to, is 1.19 10 to the negative 6, which, what does that mean? Bottom line, your PFD average is 0.019, which is a still 1. Okay, so how do we make it safer? Yes, our 1 out of 2s have better safety, well, a little bit, not very much, but it comes at a cost of a much higher false trip rate. Just look at those numbers. So what happens now? So you're saying, we can get a little more safety, not a lot, but it's a higher trip rate, and then all of a sudden your boss walks in and says, well, I need this to be a still 2. What can you do? Well, what other designs could you then implement if you want to really increase your safety? Well, let's look at a 1 out of 2 final element design. So instead of just having 1 valve, 1 actuator, 2 solenoids, we are actually separating it and doing 2 valves, 2 actuators, 2 solenoids. So these are all acting out of a 1 out of 2 system. Yes, this is a more costly solution, but let's run the numbers. Just look at that safety. So rerunning the calculations, our false trip rate is 1.48 10 to the negative 6 failures per year. What does that mean? $6,482. But look at the safety. Our dangerous failure rate, the one that everybody pays attention to, 1.35 times 10 to the negative 7. What's that bottom line? What does that mean? 0.0021 PFD average. That is a still 2. So yes, it might be more money installing this, might be more costly to run this, but a dramatic drop in safety. So as I said, you didn't have to remember the numbers. Let's compare them all on one spreadsheet now. So first of all, we have our simple 1 out of 1 design compared to our 1 out of 2 solenoid, the second design that we looked at. If we compare, let's do safety first because that's what everybody cares about the most. Safety, we went from 0.196 to 188. Okay, that helped a little bit, not much, and you can tell it's not much because they both still stayed in that still 1 range. So it does impact safety, it does improve it, it does help the design, but slightly. and at what cost? A large increase in that false trip cost per year. That it's almost double the cost. So a tiny bit of improvement, double the cost. Ouch. That's not necessarily the best. There are always going to be times and applications that it is needed, but let's look at what else we can do. What about that 1 out of 2, but we're adding that quick exhaust valve? So let's look at that safety again. Okay, it's a little worse than the solenoid, just the solenoid safety, but it's still better than that simple 1 out of 1. Once again, not really much improvement, tiny bit, but that's not going to take you out of that still 1 range. And it's even higher. So as you can see, the costs are just going up where the benefits are seeming to be missed. Now, once again, we know that there are some applications where you need to have a quick exhaust valve. But if you're just relying on that to drop your safety without adding to your false trip rate, this might not be your best plan. What about that 1 out of 2 assembly? So now we're looking at that whole separated 2 valves, 2 actuators, 2 solenoids. Now with everything in life, there are pros and cons to this situation. As you can see, we dramatically improved our safety, even to a wholesale level improvement. But at what cost? An even higher false trip rate. It didn't double again, but it is the highest of all 4 assemblies that we're looking at, all 4 architectures that we're looking at. So you need to weigh this in your application, in your environment. You know, maybe that improvement of safety is worth that false trip rate. You know, the goal was to achieve that still 2 rating that your boss wanted. Is that what you want? But there are other ways that you can improve your safety without just increasing the false trip rate and the cost. So, as I said, this is our first webinar in the multiple series, and that's what's to come. So in the next few webinars to come, we're going to go over different ways you can improve your safety without the major rises in false trip costs or your false trip rate. Our next webinar is going to feature the risks and the values of partial stroke testing. And again, we're going to use examples and calculations with that. And that's going to be in 2 weeks, in the end of September. And then following up after that, we're going to do the value of pre-engineered assemblies and how now actually you can use the pre-engineered assemblies to benefit you in your safety and reliability in your calculations. And we'll show you how you can do that in October. So there's a lot of exciting things to come. And as I said, this is just the beginning of all that we're going to be talking about. So at this time, I'm going to take questions because as I predicted, I went on a roll and forgot to stop to take questions. So if you have any, please feel free to let me know. And if you don't think of them now and think of them later, let me know by email. And below my email address, there's also links to both our resources, those books and webinars and white papers that I was telling you to check out that can be really useful. And then if you have more questions, you want more information, you've loved this and want to know all about it, you can come back. We have trainings, we have online trainings now available, even self-paced, and check us out and figure out what we're doing. We always have latest and greatest seminars, webinars, white papers coming up to keep you involved in functional safety. Okay, so we have one question now asking how to achieve a sill-free for that scenario. And at this point, we're not going to get into that. We could change some of the assumptions. We can go through a whole exercise. However, For this main broad view for this webinar, we're going to stick with the assumptions. If you want to achieve a SIL 3, there's probably a lot of different cases, and you need to know your application. You need to know exactly what's going into this. And we can talk more about that if we know specifically what's going on. But on this general broad scope, we're not going to dive into that yet. We're going to get more into that with when we cover into partial stroke testing and the pre-assembled valves as well. So we're not quite there yet. You're a little ahead of our webinar curve. The next question we have is, would a variable speed drive in a valve assembly affect the safe and the dangerous failure rate? Absolutely. Any device that is going to be used in the functional safety, it can, if it prevents or could lead to a potential dangerous or safe failure, it needs to be included into this. And you can, as I showed you with the quick exhaust valve, there could be other elements, just like you said, the variable speed drive, volume boosters. It can be as extensive as you need it to be to cover whatever you need. But if you're using those devices, make sure you have them in your calculations. The next question I have a failure rate report from a manufacturer of a certification company, of a European certification company, and I don't have any safe failure rates. Where do I get that number? Well, I can't talk for everybody's information, but I can definitely talk from my information. So first of all, your safe failure rate should always be on the certificate. And if it's not on the certificate, I would start asking, well, why not? Was this not evaluated for a low demand rate where there could be some safe failures? Was that not in the context of their evaluation? But I know for every exida certification, we have not only the safe failure rates on the meter reports and on the certificates. And if you do have a product that's missing the failure rates, ask to see if it does have a calibrated FMEDA report. Those should always have that. If not, you can always have an FMEDA done for your product that you need to get that safe failure rate or a certificate. But that, hopefully, all of your certificates have that on them. I know if you use any of Exida's, you'll definitely have that safe failure rate. The next question we have, are there not a single valve assembly that can achieve SIL 2? You had to use 2 valves in your example. Yes, there are. However, for the general assumptions, for the general purpose, we just kept to the SIL 2 with the 2 valves for this. If you have more information, if you have specifics, it's much easier to narrow down those calculations and achieve what you need to, especially if you're incorporating things like our next webinars we'll talk about, like our partial valve stroke testing, shorten your mission time, or if you're using pre-engineered assemblies. Those all can help you achieve your SIL 2 for a single valve. However, when we're talking pretty generics, we're just going to stick with this. But if you want to get back to me, I can certainly look at your specific information and get you a better idea. But there are definitely valve assemblies with a single valve that can reach SIL 2. But they're a little harder to come by, or you might have to do some more work for it. Now there are no other questions. If you have any others, Feel free to reach out to us. Reach out to me and let me know. Thank you so much for joining us today, and hope you have a great rest of your day.